Good evening, everyone. Welcome to the tutorial session of course Introduction to Robotics. Today, we'll discuss questions based on the week 12, like the lectures given on the NPTEL tutorial. In the week 12, we'll solve some questions related to that, and also we'll see some of the basic concepts related to that, like path planning and localization algorithm. So, we'll start with the first questions. The first question asks which of the following can be used for position tracking. So as it is taught, the Kalman filter, extended Kalman filter and particle filters are used for the position tracking of the robot. And we will see like which method is used when. So Kalman filter is used for linear system and extended Kalman filter uh, is for both the linear and for the non-linear system as well. That is the extended version. And after that, the particle filter, it can handle non-linear, linear and non-Gaussian systems as well. All three have its own advantage and own application. So for linear systems, Kalman filters can be used for tracking position. For linear and non-linear system, extended Kalman filters can be used. And for like particle filters is used for linear, non-linear or Gaussian, non-Gaussian system as well. Oh, sorry, I was on mute. So in the first question, it was like which of the following can be used for position tracking? So the options are Kalman filter, extended Kalman filters, and particle filters, and binary based filters with a static state. So for tracking the position, Kalman filter and extended Kalman filters and particle filters are used. They have their own area where they can be used for the position tracking. For linear system, Kalman filter is used. Extended Kalman filter is like the next version of Kalman filter, which can track the position for the linear and non-linear system. And third is a particle filter that can be used for the linear system, non-linear system, as well as non-Gaussian system. So for the option one, A, B, C is the correct answer. For the question one, option A, B, C is the correct answer. So the second question is, it's a true and false question. Particle filter can be designed to recover from an erroneous belief distribution. So the answer is true. Like by periodically resampling the particles randomly, it can be designed to recover from the erroneous belief distribution. So, like in resampling, what happens? Particles with higher weights have a greater chance of uh, surviving, while those with lower weights are removed or replaced. The process maintains uh, among the particles. And the final estimated state, that is the position and orientation, is calculated typically as the weighted average of the particles. So option A is the correct answer for this question. The third one is the Markov localization algorithm is computationally more expensive compared to the Kalman filter. Yes, because the Markov localization algorithm has to update the probability of all positions within the whole state space at any given time. So the correct option is true. Uh, we can revisit through the slides so that we can understand more. So, like Markov localization address the global localization problem and the position tracking problem, and also like the kidnapped robotic problem. So we'll see. Markov localization is used for global localization problem, tracking the position, that is the position tracking problem. And the third one is the kidnapped robot problem. What is kidnapped robot problem? It is like during the some time instance, uh, we don't know the like motion of the robot. So what will be the current position and orientation that we have to estimate? So that will be difficult if if the tracking is lost for few time instances. So that problem is also solved using the Markov localization algorithm. And this is little computationally expensive than the simple Kalman filter algorithm. So option A is the correct answer for this question. We'll move on to the next question. Actually, it update. You can write this line also. It updates the probability at all the space, like all the position within the whole state space given at any time. So it will be more computational expensive. And the probability where is the finding the robot chance is higher. That is estimated as the current position of the robot in this algorithm. So it updates the probability of all position within the whole state space at any given time. So next question is, it is the assertion and reason based question. So in this, it is asking the Markov localization algorithm can address the kidnapped robot problem. So we have seen that it can address. And Markov localization algorithm use both map and current version to update its beliefs about the state. So we will see the formula for this Markov localization algorithm. Then we can conclude whether it needs the map information or not. So the input given, like the variable which is needed by Markov localization, like in the algorithm we can see, it requires belief of x t minus 1, then the current action that is ut, zt is the current measurement, and m is the map information. Okay. After that, it estimates where the robot will be. So it requires the map information to estimate the robot position. Like let's see the formula. So belief of xt bar, that is estimated position, is given as probability of xt such that the current action ut, the last position xt minus 1, and the map. So here you can see it requires the map information and belief of xt is equal to eta into probability of zt, like measurement at that time stamp, and the position xt and the map information and belief bar of x2. So the Markov localization algorithm use both map and current observation. So the current observation is zt. So it it needs both zt, m, ut, and the previous position. So it requires these four parameters to estimate the current position of the uh, to localize the robot. So in this, both assertion and reason are true, and reason is the correct explanation for this question. So the option A is the correct answer. Like whenever a map is given, let's suppose this is the map of an environment. Like this is a path, and we have a map made, and there are lots of landmark is there, like trees, traffic sign. So whenever our robot is here, let's suppose, and this is the origin of map. Like this is 0, 0 and 0, x, y, z. So when the robot is moving in this direction, let's suppose robot came here. So this is the robot position, that is x t minus 1 at time stamp t minus 1. So when robot is here, then how it will match where it is. So now robot is here, robot have some sensor. Let's suppose this is some sensor. So it scan the area, and let's suppose this landmark is scanned. This pole is scanned, and robot get to know that it is at some distance with some direction. Like let's suppose v bar is the vector. So it is v bar far from the landmark. Let's suppose landmark. This is T. So now, how the robot will estimate its position? Because see, this landmark T have its own position with respect to the map. Okay, so this is just a vector addition problem. See, landmark T is at, let's suppose this is A bar and this is B bar. So what is the position of this one? This will be A bar plus B bar. Like let's suppose this is the XT bar. So the position of robot is A bar plus B bar. So in this question, we need the map information. As you can see, this position of this landmark, like this signboard or the pole it is there, that is with respect to the map axis. So we need the map, and also we have scanned this pole, so that is the measurement. So we need this map, measurement, and also we need the current action, like how much far from the previous it can move, and the last position of the robot. So these four things are used. So option A is the correct answer for this question. So we'll see the next question. So which of the following are true about the breadth first search algorithm? So it assumes that the edges weights are equal. Yes, this is the correct. We'll also see the algorithm. The second option is it is a complete algorithm. Yes, it like explore all the nodes in that map. Third is find the shortest path between a given source node and all other nodes in a graph. No, this is not correct. And it explores all the nodes at the same depth here level before moving to the next depth here level. Yes, this is correct. So A, B, D is the correct answer. We'll also see about this breadth first search algorithm. Like let's suppose we'll take the example which was taught in the classroom. So this is our source. Okay. So first what it will do, it will go to the nearest node, this one and this one. So for this, this will be the one, two, and then after going to this node, it will go to the next first node here, and then this will be deleted in this, and this will become our one. Okay, and this will become two. Now after traversing this node, it will go to this node. So this will become first now. Now, if it gets the destination point, let's suppose this is not the like this is source, this is not the destination point. Then again, it will go to the next node, that is the first node. We will go here, and for this, there is only one node to explore. This is the one. After this, it will go here. For this, these two nodes are the node to be explored. So let's suppose this is the destination. If it finds that this is the destination point, then again it will back traverse. For this node, this is the parent node. This is the parent node for another one, and this is the source node. So again, it will backtrack, and also it will find the uh, like position from, like it will find the trajectory from the source to the destination. So breadth first search is complete, but depth. So this is a complete algorithm. So option D is correct. In this, it assumes that all the edges are equally weighted. So it traverses all the nodes without like giving any weight to the some specific node. Giving weight means like if node have some higher weight, then that node to be traversed first. But it does not do like that. So for this, A, B, and D is the correct answer. So now we'll move on to the next question. So Dijkstra's algorithm can find shortest path between a given source and a target node with arbitrary edge weights. And the reason is that each visit to node, the algorithm tries to update the minimum distance to reach that node from the given source node. So for this, like it tries to update the minimum distance to reach that node from the given source node. So the reason is correct, but the assertion is false, and it is not the correct explanation because the assertion is itself false. So the option C is the correct answer for this question. Just let me check whether this video is recorded on. Yeah, it's recording. So we'll solve the next question now. That is, select all admissible heuristics from the option provided below. Using each of these admissible heuristics and the information provided in the table below, use the A star search algorithm to find a path from the start to goal for the grid world shown. You can take Gx to be the number of steps taken to reach the grid cell X from the start state and assume that the robot can only move into adjacent cells, like to the left or right. So you can move only in the adjacent cells, like located above, below, or the left or the right of the current position. So we have to find the optimum path from the source to destination in this question. And this is a grid map is given, like this is our goal position and this is our start position. So from here we have to reach up to the goal position. So how many cells does the A star search algorithm visit to find the goal state? Select all the answers that are possible for all admissible heuristics. Include the start and goal states in your count. So before moving, we'll see some one example that was covered in the lecture. After that, we'll solve this question. Let's suppose this is our starting point. And start is this and goal is this. So we have to start from the starting position and reach to the goal position. And we all know that the cost incurred is Gn plus Hn. So Hn is the heuristic cost and gx is the number of steps, like it is the cost from reaching to the grid from the starting grid. So gn is written in black uh, pen, like 1.5 is the gn, here is the 2, sorry, here it is 2, here it is 3, 4, 2, 3, 4.5, and h value is given, that is heuristic cost of ha is equal to 4, hb is equal to 2, hc is equal to 4, h of e is equal to 2, and h of b is equal to 4.5. So first we'll calculate f of a. So for f of a, gn is, this value is gn, like g of a you can say. So g of a plus h of a, that will be 1.5 plus 4, that is equal to 5.5. And also we'll calculate for fd. For fd, this is equal to gd is equal to this 4.5. So that is 4.5 plus 4.5. Sorry, it is, this value is 2. So 2 plus 4.5, this is 6.5. So here FA is less than FD. So now we will move into this direction. Now we'll again go to B. So FB is equal to, so now GB is equal to here, like it is the cost from coming from S to B. So now for this node B, GB is equal to this 1.5 and 2, both will be added. So that is equal to 3.5. That is equal to GB plus H of B. So that is equal to 3.5 plus 2, that is equal to 5.5. And still FB is less than FD. So we will go this direction. Now we'll check FC. FC will be GC plus HC. Now GC is 1.5 plus 2 plus 3. So this will be 6.5. This is equal to 6.5 plus HC is 4. That is equal to 10.5. Now you can see FC is greater than FD. So in this case, now we will try to move towards the E, from D to E, because FD is less. So we will take the less cost path. So now FE is equal to G of E plus H of E. And G of E is 2 plus 3, that is equal to 5. So this is 5 plus 2, that is equal to 7. Now f of E is less than f of C. So again we'll move from E to G. Okay. So the final FG is equal to G of G plus H of G. So H of G is 0, because for source and destination it is 0. So this value is 0, and G of G is G of D plus G of E plus G of G. So this is equal to 2 plus 3 plus 2. This is 7. So we have got the path. Now the parent of G is E, and the parent of E is D, and the parent of D is S. So we can back traverse and we can get the optimum path having the less cost using A star algorithm. So now we'll solve this question. So here the Euclidean distance is given like here from 0, 1, 2, 3. Okay, so we'll see this question now. Huh. So in this question, the Euclidean distance from the start state to every grid cell is given. Like this is from 1 to 1 is given 1.6. This is 2.48. Like that for every grid cell, it is given from the start state to the every other grid cell. So let's suppose this is our start and we have to reach to the goal position. So first, the algorithm come to the next node and it will check the least cost trajectory or least cost path, and then it will go to the next node depending on which is the least cost, and then either it can choose this path or either it can choose this path because it can choose only the adjacent as mentioned in the question that a robot can move into the adjacent cell. So here you can see how many it is asking how many cells does the A star search algorithm visit to find the goal state. Select all the answers that are possible for admissible heuristics. So from moving to here, like how many nodes, how many grids it will search that A star algorithm. So the grid it will start from this 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is the total grid 0 to 10. So total number of grid is 11. So we're just asking the number of cells this A star algorithm is visiting. So that is 11 for this question. And also we can calculate the cost depending on the each path, how much cost it is, and the least cost path will be chosen by the A star algorithm. So the next question is, which of the following is most suited for the global position? Like for global position, the particle filter is the most suitable one. The Kalman extended filters are for the local position. I think these questions we have already visited, but only the options are little changed. So second one is Markov localization is an instance of a Bayes filter algorithm, and Markov localization does not assume the availability of map. So as we have already discussed, Markov localization assume the availability of map in the question number 2, and it is the instance of a Bayes filter algorithm, as you can see with the formulas, probabilistic formulas of this Markov localization. Here you can already see it depends on the map. So the assumption is true and the reason is false. So option C is the correct one. Which is the correct algorithm for recursive map traversal, which extends till one of the node is exhausted and moves to the successive nodes. So this is the breadth first algorithm. It it is a complete algorithm and it moves to the successive node only when the one of the node is exhausted. So the option A is correct for this. So today we'll stop the lecture here only, and this video is recorded and uploaded on YouTube, and the link will be provided in NPTEL portal as well. So maybe the next class will be the class on the some of the question of the whole course, some of the important question we will discuss an important concept. Maybe the extra class, don't know whether they will keep or not. So we'll discuss tomorrow. Thank you everyone for attending today's lecture. Yes, you can ask Ram Kumar. Yes, sir. Regarding the last question, uh, if we have heuristic options. So the heuristic options was so what does the heuristic options? It depends on the dynamic cost. Like let's suppose some that if the environment is dynamic, so it depends on the dynamic cost. So the total cost for moving from one position to the another depends on the Gn plus Hn. And Gn is the cost, like let's suppose what will be the Gn of this node E. So Gn is the cost of node E is the cost from the starting node S to E. Like while moving from the S to E, what is the cost incurred? So that will be G of N is equal to G of N minus 1 plus G of N minus 2 up to plus G of 1. And this H heuristic cost is the dynamic one. So you have after let's suppose this is our first node. I will take other color pen. So this is our first node. We are taking in this direction, second and third. Okay. And start is the zeroth node. So G of C. So C is the third node. So G of 3 is equal to G of 2 plus G of 1. So that is equal to 2. Here this is 3 plus 2. Okay. And also plus up, this will go up to G of 0. Sorry. Okay, sir. So for this one, we directly take the value that is the G of n. What? Which when we calculate heuristic h of n respective cell will be taking value directly. We have to take from that cell, like if you have to move E to G. So now we will see what is the heuristic cost for moving to G. We will not see the previous heuristic cost because that is the dynamic cost. So we will see for the current instance only what is the heuristic cost. So like that we have to do. Okay, sir. So in this question, they have given one box, sir. Median distance can start straight to every case. So this will be H of n or this is G of n, G of n. So it will be G of n. Yes, yes. From moving from like it is distance from a start state to every grid cell. Okay, so since the question they have only asked you what are the possible. Yeah, yeah. So first it will start from here and then it will go this direction. This is 1.6. Again, it will go up to the next one that is 2.8. Like this will go to the first one, then I go to 2.48. Now it will see this 2.48, 2.48 is equal, so it has the choice to take any other node. It will take this 3.16. Now this G31 is less than G of 1, 2. Sorry, greater than 1, 2. So now this will search this grid. This is 2.48. Again, this will search this grid 3.16. Now it will again search the next grid, that is 3.70. So G of 2, 3, that is equal to 3.70 is equal to G of 3, 1. So now it have both the choice. So like sorry, here first it will compare with G of 3, 1. That is 3.16 only. It's not 3.70. It's not equal. It is less than. It is greater than G of 3, 1, that is equal to 3.16. So now it will again go up to here. Now it have both the choice from here to go to the destination. So it will cover all the nodes. Here you can see first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10, 11. So total 11 grid it will go, and the sequence will be like this: 1, 2, 3. It can take 4. It can take fourth in any direction because both the values are equal. Then again we'll take the fifth one is here, then sixth, and then this is 3.16. So both that is greater than 2.48. So this will be the seventh one. Now this is the eighth. 1 minute. How many is 10 or 11? How many cell does the A star algorithm visit to find the goal state? So it is taking, this is the start cell, first, second, third, fourth, fifth, sixth, seven, eight, nine, 10. So it only have the 10 cells it is visiting. So the option will be 10 here. So it will see what is the cost incurred, and after that it will move to the next cell. If it is less than the previous one, let's suppose if the cost, there is two paths. So if the cost in the path 2, like the final cost is given by F only. So if greater than the path 1, then again it will start following the from the path 1 to goal. If it is less than path 1, then it will follow path 2 through the goal. Like this. We'll choose the lesser cost path. If you are asked what are the total paths followed, then we are going in all the cells. No, not all, not including all the cells. We could have reduced some of the cells. Like let's suppose here the value is given like 4.0 instead of 3.70. So let's suppose the robot move here 3.70. Okay. So now, sorry, let's take it 4.3. Let's little greater than the final cost. This is 4.3. So now the robot move at 3.70. So it will compare with this. It is less than 4.3. So it will move to 4.2. And this is the least cost method. And so it won't travel this grid. So there will be answer will be less than one less. But here, whenever the condition check situation came, like at every condition check situation, we can see both the grids are equal. So it had to travel both the grid to find the cost. Here also it is equal, here also it is equal. That's why it travel in all the grids. Like in the down example, you can see first it went up to C to G discarded. So like that, we have to see what is the cost, and accordingly we can discard. But you need to count the remaining between users. Ah. For example, because to you have the report that also be counted. Like in this question, it is asking how many cell it have traveled. So in this question, we have also traveled all the cell. We have traveled C also. Like we'll travel this, and this, and this, S and G always included. So we have traveled all the cells. But in some case, if the cost to some path is too high, so we should not travel to that. Okay. So this video will be uploaded on YouTube. Thank you everyone for attending today's lecture.